Hello and welcome. You might be surprised to find that the study of algebra actually begins with a study of the language. But that's actually where we have to begin. Because in algebra, we are discussing and quantifying and displaying and manipulating quantifiable relationships between things. And in order to be able to describe those quantifiable relationships between things, we have to be able to do those descriptions precisely and accurately. And so we start off with a discussion of what we call order of operations. So what I'd like for us to do is to first of all take a look at your warm-up problems, which you'll find on your activity sheet, which you should download and print off in association with this particular video. And I'm going to give you about 45 seconds to do those 4 problems there. That should be pretty straightforward. So take some time to do that. Welcome back. So hopefully the problems that you did here were actually pretty straightforward. As you can see, I'm showing the answers right now, and hopefully those things were not too difficult. They were pretty straightforward, and if there were mistakes, you were able to correct them pretty quickly and easily. So let's take some time here. I've probably introduced this concept in class by now, and so this is not unusual for you to see this. Let's take some time for ourselves to empty our minds of all thoughts except for the present moment. Let's take a minute to do that, please. Welcome back. Let's start the process of learning the language of mathematics. And by doing this, I'm going to show you a problem right in the center of the screen here, and it shows 2 mathematical operations taking place. And I'm going to have you try and solve this in 2 different fashions based on a central question here. Do we do the subtraction first in this problem, or do we do the multiplication first in this problem? I think you'll find that if you do the subtraction first, you have 18 minus 5, that's 13, multiplied by 2, that gives us an answer of 26. And if we do the multiplication first, we have 5 times 2, which is 10, subtracted from 18, that gives us a value of 8. So which one of these is correct? Again, we have to be able to describe patterns and relationships precisely and accurately. So we need a set of rules to be able to describe which things are done first. What exactly do we mean when we say 18 minus 5 times 2? Well, as it turns out, our convention that we've adopted is actually that the multiplication is first. And in fact, if we want to do the subtraction first, we have to place that subtraction inside some parentheses, which override our usual rules. And this specifically says that the 18 minus 5 has to take place before the multiplication by 2. There's some other things that I want to let you know about multiplication. The fact that multiplication is before addition and subtraction is to some extent made easier by some notational things that we sometimes do. 5 times 2, 5 in parentheses, 2 in parentheses. Those two things have no operation sitting in between them. Yes, they're inside of parentheses, but within those parentheses it's just a single number. There isn't anything that's going on inside those parentheses. But what's most important here is that there's no arithmetic sign between 5 and 2. What does that mean then? It means multiplication. This also means multiplication. And in the same way, this means multiplication as well as this. We use a dot sometimes to describe multiplication. Why do we do that? Here's the reason. Because sometimes when we are describing patterns, we are making use of what we'll find are called variables. Our most common variable letter is x, and using an x with a multiplication sign, that looks like xx, and so sometimes that looks a little visually confusing. So we've adopted within the larger mathematical community the use of the dot as another way of describing multiplication. Something else to keep in mind here. In the next one, I'm showing you 18 divided by 3 times 2. Now, in our previous one, we found that multiplication was before subtraction. And we actually described the fact that we sometimes compact two numbers together if they're being multiplied as a way of describing the fact that this is done first. In that sense, it might be a little misleading here, because it looks like the 3 and the 2 multiplied together is actually first. In reality, that's not the case. Multiplication and division have equal priority, which means that we simply go from execute from left to right. That should say left to right there. I'm going to change that. Actually, that should say left to right. So multiplication and division have equal priority, and so we should execute these things simply from left to right. The 18 divided by 3 is done first, which is 6. Multiplied by 2, the answer is 12. Thank goodness we know that, because if we did the multiplication first, 3 times 2 is 6. 6 divided into 18 is 3. It's a different answer. So it's important that we know which one is first. And in this case, the division is first, and so the answer is 12. So what are these order of operations? You've already seen that multiplication and division have equal priority, and so they're executed from left to right, and you've also seen that multiplication happens before subtraction. You've also seen an instance of parentheses, where I've shown you an example of how parentheses can override the normal order of operations. So what exactly is the order? As it turns out, parentheses are first, multiplication and division have equal priority, they're executed second, and then lastly we have addition and subtraction. Addition and subtraction also have equal priority. If you have a sequence that's just pluses and minuses, those have equal priority and are simply executed from left to right. Something else to keep in mind here, and I haven't shown you this yet, but perhaps you've seen it before. Exponents and radicals. You've seen exponents perhaps in Einstein's famous equation E equals mc squared. That little 2 in the squared is an exponent. It has to do in this case with 2 to the 4th power, 2 times 2 times 2 times 2, 4 2's multiplied together. The square root is actually the opposite operation in that regard. The square root of 4 is whatever number multiplied by itself equals 4. 2 times 2 equals 4, so the square root of 4 is 2. The point here is that exponents and radicals are done after parentheses, but before multiplication and division. So there's actually 4 tiers that we work with here. Parentheses, exponents and radicals, multiplication and division, addition and subtraction. And within each one of those 4 tiers, all that you see there has equal priority. And the way that we usually summarize this is with an acronym that simply says, please excuse my dear Aunt Sally. PEMDAS, parentheses, exponents, multiplication, division, addition, subtraction. Something that, it's actually a mnemonic that describes a pattern of order of operations which we will be using throughout this course. So with that in mind, let's apply these things to an example. I have 16 minus 5. There's a 2 in parentheses there. What's going on between the 5 and the 2? It's multiplication. So 16 minus 5 times 2 divided by, in parentheses, 4 plus 6. We refer again to our order of operations. What's done first? The parentheses. 4 and 6. 4 and 6 are added together to give us 10. There's also a parentheses around the number 2, but there's no operation inside there. It's just the number 2, so there's nothing really there for the parentheses to do. They actually don't do anything. So what's next is the multiplication that takes place between 5 and 2. 5 and 2 is 10. We rewrite everything else around it. That's important. You will see when we are evaluating these things that we only do one part of it at a time, and we rewrite everything else around it. That allows for us to do this in the correct order. So I want you to get in the habit of doing that for yourself. 16 minus 10 divided by 10, what has priority? The division. 10 divided by 10 is simply 1. 16 minus 1 is 15. Our final answer is 15. So with that in mind, I'm going to give you 3 problems to do. They're on your activity sheet. I'll give you 2 or 3 minutes to do them. Please work on those now. Welcome back. Hopefully those problems are pretty straightforward. If not, then take a moment to rewind the video a little bit, go over some of the concepts again, go through the example that I provide there. I think once you see exactly how those things work, then the examples will be all the more straightforward and you'll be able to troubleshoot exactly what you did incorrectly. I mentioned beforehand that we have multiple ways in which we describe multiplication in algebra. I'm showing you the most confusing way here using a time sign, the tried and true old time sign. But sometimes when we're multiplying numbers and variables together, the use of the time sign can be sometimes visually confusing in terms of especially when placed right next to an x. And so we sometimes will replace it with a dot, and sometimes you'll see that since this is 3 of something, 3 times something, that's what multiplication essentially is, 3 of something, 4 of something, even half of something, that's multiplication. We will sometimes describe it simply saying 3x's, 3 times x. That's another way of describing multiplication. You've also seen some instances in which we are using parentheses either around the variable or around both the variable and the number, and even just the number. Don't worry about these. They come up sometimes. The parentheses in this case don't do anything because there's no operation inside of them. They just pop up once in a while, and sometimes they're necessary in order to be visually clear. Now, as I'm taking a look at some of these things, I want you to get in the habit of taking a look and asking yourself, what is done first? We take a look at this one. It has an exponent in it, 3 to the second power, or 3 squared as we call it. It's got parentheses in it. It's got multiplication, division, addition, and subtraction all inside of it. But the real question by an order of operations is, what do I do first? And so we mentioned beforehand, and you saw this as we were doing this before, that there are some things that we do first, and we simply do that part and rewrite everything else around it. And then we do another part and rewrite everything else around that. I've got a picture of an onion there in the upper right-hand corner, right above my head, probably. And that is a way of illustrating the fact that as we are doing some things that we do first, we're doing some operations sometimes in the center of that expression. And as we're then doing more operations, we're building more and more layers around this onion. And so oftentimes you might see me in lecture class say things like, where is the center of the onion in this expression here? That's going to be important for you to understand, because when we start solving equations, we're going to be working not from the inside out of the onion, but from the outside in. So keep that in mind as we're doing this here. Where is the center of this onion? And the answer, hopefully, that you see is, much like before, the parentheses are done first. That is the center of the onion. Everything else builds around that. So we do that first. 7 plus 5 is 12. So we've done the center of the onion. What's next? We have 3 squared minus 4 times 3 divided by 12. Exponents are next, aren't they? So 3 to the second power, that's 3 times 3, which is simply 9. And now again, we write 9, but we rewrite everything else as well afterwards. So 9 minus 4 times 3 divided by 12. We have multiplication, division, and subtraction inside of there. Multiplication and division happen before subtraction. Multiplication and division have equal priority, so multiplication in this case, since it occurs first, left to right, is done first. 4 times 3 is 12. And then 12 divided by 12, that's 1. 9 minus 1 equals 8. So another example of this. Here's another example. Now sometimes you're going to run into situations where parentheses are to some extent in disguise. I don't see any parentheses specifically in this problem here other than the one around the 2, which doesn't do anything. But in order for us to calculate what's inside of that square root sign, we've got to do everything inside of that square root sign so we know what to take the square root of. 21 minus 5 is kind of like a set of parentheses in this regard, isn't it? So, even though we don't have parentheses there before, we can kind of think of this as being a parentheses here. 21 minus 5 is 16. The square root of 16, well, we can do that first, but remember, exponents and radicals have equal priority, so we want to do the exponent to the left first. 3.2 squared, that's 3.2 times 3.2. You could do that on your calculator, that's 10.24. We then have to do the radical to the right, that's the square root, we call it a radical. Square root of 16, what number multiplied by itself equals 16? The answer is 4. So now we have 10.24 plus 4 times 2. The multiplication comes before the addition. 4 times 2 is 8. 10.24 plus 8 gives us our answer of 18.24. You can see that sometimes these relationships get pretty complex, involving square roots, multiplication, division, exponents. These things can get pretty complex, and so knowing what our order of operations is becomes absolutely vital if we're going to be evaluating these things correctly, not to mention manipulating them correctly. So along those lines, here's another problem for you to do in the notes, and I'm going to give you 3 or 4 minutes to do this. Welcome back. This is an example that actually used something that I hadn't shown you before, but hopefully it was fairly straightforward. Notice that not only is there a set of parentheses, but there's also a set of square brackets in the latter part of the expression there, the 15 minus 3 times 2. There's square brackets around those things. This allows for us to nest parentheses together. The smallest ones near the center are parentheses. The next ones beyond that are square brackets. Beyond that, we'll use curly braces, which are, I think, shift square bracket on your typewriter. So those don't pop up very often, usually just parentheses and square brackets. And it allows for us to see when something is nested inside something else. One other thing, let's actually take a moment on your activity sheet here to write down what the order of operations are. You'll notice that on your activity sheet I've given you a small section there to write down a summary of exactly how you do order of operations. Perhaps this is a place where you indicate, please excuse my dear Aunt Sally, and you describe each one of those, what each one of those abbreviated letters stands for. Perhaps some other concepts like multiplication and division have equal priority, addition and subtraction, equal priority, exponents and radicals, equal priority. Sometimes parentheses can be simply parentheses, or they can be square brackets, or they can be curly braces as well. A lot of things to write down there, but this really summarizes what we've been doing, isn't it? That's the great thing about mathematics, is that oftentimes you can take a lot of skills and ideas and work that you've been doing over a long period of time and summarize it very concisely and even elegantly in a very small space. So take a moment to do that for yourself. I'm going to give you a minute and a half to do that. By the way, you might be noticing that in the times in which I'm giving you an activity to do, I'm playing some classical music. That's not done to annoy you. That's done specifically because the research says that playing classical music actually stimulates neural activity. So it's done as a means of helping you. If it's an impedance to you or an annoyance to you, please feel free to just simply hit mute on the video when we're doing some of these things here. But hopefully it acts as a good aid. Let's make use of these patterns towards a specific context, namely looking at perimeter and area. Now, area is something that most people know how to calculate and what it is. Perimeter is not as commonly used, and so let's take a moment to describe exactly what perimeter is. I've got a polygon sitting on the left-hand side over here, and the polygon, by the way, polygon just means some sided figure, the number of sides in a figure. It could be a square, it could be a rectangle, triangle, pentagon, hexagon, heptagon, octagon, and so forth. We don't know exactly how many sides it is when we just say polygon, but in this case it's pretty clear to see that it's a hexagon with 7 sides. The bottom one we oftentimes call the base, and so I've got that labeled there. But even more significantly, I've got numbers around the polygon describing the lengths of each one of those sides. And the perimeter is simply how long something would have to be if you were to create a fence around this polygon. It's the distance around the polygon. So you can see that it's pretty straightforward on how to calculate that. We calculate the perimeter P by taking all of those lengths of all of those sides and simply adding them up. 9 plus 4 plus 5 plus 7 plus 7 plus 5. And as it turns out, the answer to that is simply 37. So that's the concept of perimeter. Let's see how it applies to some perhaps more common polygons, namely a parallelogram. A parallelogram you can just think of as a rectangle that's been tilted a little bit and its right angles suddenly failing from lack of support, evidently. And so it still has opposite sides that are the same length. Opposite sides are also still parallel to one another. But the angles are not necessarily right angles. They actually could be right angles. All rectangles are parallelograms, but they don't have to be right angles. More importantly here, we can describe the lengths of each one of these sides. You can probably think of it here as simply 3 plus 7 plus 3 plus 7, and we have our perimeter. The answer there is 20. But if I label each one of these things with letters instead of numbers, B's for bases, S's for sides, can we describe in a concise formula the pattern that we see here for perimeter? Perimeter here is simply B plus S plus B plus S. Those are letters you don't play with. B plus S plus B plus S, or a simpler way of describing it is 2 times B plus 2 times S. This is a formula that describes the relationship between the base and side of a parallelogram and the perimeter of a parallelogram. It's true always, 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 always. And we can quantify it and describe it in a small, elegant type of framework known as this formula. This is the joy of algebra. Let's try doing this for a rectangle. In this case, the bases and the sides are replaced with a more common term, length and width, described here with L and W. But actually for a rectangle, which is simply a parallelogram in which all the angles are right angles, our formula for perimeter is actually identical to the one before. It's just that this time it's 2 times length plus 2 times width. That makes sense based upon experience. And you can see here once again, we are able to describe a relationship, a pattern, in a concise format using variables. It's even more straightforward when we're talking about a square. Now it's just not opposite sides that are equal, but all 4 sides are equal. The length of a side is simply S. And so a rectangle with all sides equal is how we define a square. And we can describe the perimeter of the square very simply, S plus S plus S plus S. Well, there's a more simplistic way of describing it, isn't there? It's simply 4 times S. So we have formulas for perimeter. So take a moment on your summary sheet to write down what those formulas are. I've got a place near the bottom of the first page for you to do that. So take a moment to do that. Right now it's time for us to use some of these formulas. Let's first of all take a look at our first problem. Find the perimeter of a parallelogram with a base of 16 inches and an adjacent side of 8 inches. We can make use of our formula, which is simply 2 times the base plus 2 times the length of that other side. 2 times 16 plus 2 times 8. Order of operations once again. 2 times 16, 32. 2 times 8, 16. We do each one of those individually. This is actually an onion with 2 centers, isn't it? We do one, and we can also do the other. Now we do the addition. 32 plus 16 is 48 inches. That's the perimeter of this parallelogram. So actually do this problem on your own. This is also on your activity sheet. It's number 9, so take a moment to please do that. Welcome back. This is a good example of a problem that is served well through a first step of drawing a picture. And hopefully I've modeled that fairly well, as I did here with this particular problem here. It's so important that you draw a picture. So much of mathematical understanding is simply drawing something out. I cannot tell you as a math instructor the number of times in which students have struggled with a word problem simply because they weren't able to visualize it. The act of drawing it out, the process of drawing it out, actually makes it so that the problem is suddenly visualized, and a difficult word problem suddenly becomes an easy word problem. So I would encourage you to get in the habit of drawing a picture first and then taking it from there. Here's another problem that involves a chain link fence. So once again, make sure that you draw a picture before solving this, but take a moment to do this as well. I'll watch the time. Welcome back. You might have noticed with this particular problem that we made it perhaps somewhat realistic by making it so that after calculating the perimeter you had to subtract a little bit of space for the doorway. After calculating a perimeter of essentially 110 meters, you had to subtract off 3 meters for a rather large doorway. So here's the third one here. How much aluminum edge molding is needed to surround a stainless steel kitchen sink that measures 40 centimeters on each side? Take a moment to do that as well. Welcome back. Perhaps in this problem, as well as the previous ones that we've been doing, you might be developing a good set of steps as far as how to solve word problems. Let's see if we can describe and systematize exactly what those steps are. What's important here, and you might want to take notes on this as I've given you some space at the bottom of your activity sheet to do so, is the first thing that you're doing is essentially figuring out what is the question that's being asked here. And in order to do that, you really have to draw a picture. That's so helpful in defining exactly what the situation is and what the question is that's being asked. In this case, it's the length of molding that's going around a square stainless steel kitchen sink. The second thing is what's known. You can actually label that picture with the things that are known. Just like we did here. We labeled one side of the square. We knew that it was a square, so we only needed to label one side as being 40 centimeters in length. The third thing, what's an important relationship that's involved here? Well, if we're finding how much molding to purchase, that's a perimeter question, isn't it? The distance around the sink. And the formula for perimeter of a square is simply 4 times the length of one of the sides. We then calculate our answer using the desired formula. 4 times 40 equals 160. Now the last step, it feels like we're done, but we actually have one more step to do. We have a number, but we don't know how that number necessarily applies to the problem. 160 what? And the answer is, that is the interpretation of it. The molding is 160 centimeters. A unit is important here as well, isn't it? Let's interpret the number and apply it back to the problem. The molding is 160 centimeters. So those 5 steps are absolutely vital in figuring out exactly how to solve not only word problems, but really any problem in math that you're going to be handling throughout this course. So take a moment to write those down if you haven't already done so. Welcome back. Let's take a moment to apply this same set of techniques towards not perimeter, but area. Let's give you an example here. I have a closet that needs some new carpeting. How many 1-foot carpet squares, those little 1-foot carpet squares that you can sometimes purchase in packages, how many of those 1-foot carpet squares would be needed to carpet a closet of the size shown? It's obviously a rectangle there with length of 5 feet and width of 3 feet. Well, it would be approximately 5 rows of 3 or 3 rows of 5, however you see it, with a total number of squares of 15. What if the closet were 4 feet by 7 feet? Then how many squares would be necessary? What is the pattern here? And the answer, hopefully you can see, is that length times width gives us the area of a rectangle. Always, always, always. So again, we can describe this relationship using this formula. So you can see it there. There's also a place on your activity sheet to write that down. Let's take a look also at a parallelogram. And in this case, it's a little bit harder to visualize exactly what the size of the area is here, but I actually have a little bit of an animation to show you here. Remember, our 2 lengths that I'm showing you here are, first of all, the base. That's the bottom side that I'm showing you here. And instead of showing you the length of another side, I'm showing you the thickness, the vertical thickness of this parallelogram. It's what we call the height. We symbolize it with h. So that's important here. We're not using the length of one of those sides, so to speak. We're using the height. And here's why. I want you to watch this animation here, and you can see that if I take this somewhat purplish rectangle and I move it from one side of the parallelogram to the other, you'll see that I can actually make an equivalent sized rectangle, a rectangle of the same size as the parallelogram. And for a rectangle, we already know how to calculate its area. Well, what's the distance of one of those lengths here? Well, it's a little hard because it's been chopped up a little bit on the bottom, but in particular on top, it hasn't really been chopped up. It's still the length of that base. And what's the width of that rectangle? Well, it's now this new thing called the height of the parallelogram. So the base of the parallelogram is the length of the rectangle. The height of the rectangle of the parallelogram is the width of the rectangle. Say that 5 times fast. So instead of length times width, we have base times height. That's the formula for the area of a parallelogram. Always, always, always. And we can actually make use of this here where we have this particular parallelogram. So take a moment to make use of this formula. So take a moment to make use of this formula as you solve it for the area of this particular parallelogram, and try to find your answer there in square inches. Take a moment to do that. Welcome back. This is a good example of a problem in which more information than necessary is actually provided. I'm giving you not only the height of that parallelogram, but also the length of one of its sides. And that was actually designed in an effort to trip you up a bit. That side of 8 inches is not necessary in order to solve the problem. And in fact, if you use it, you get the wrong answer. It is base times height, 16 times 7, or 112 square inches. Lastly, let's take a look at volume. With volume, we're looking at capacity. We're not looking at molding around a room or carpeting in a room. We're now taking a look at the amount of air that's inside of this room. And it's measured not in terms of square inches or square feet, but now in terms of cubic feet or cubic inches. A cubic inch would be a cube that's 1 inch wide, 1 inch tall, and 1 inch deep. So for this particular rectangular prism, which we call just something that's almost like a cube, but it's actually a rectangle on some sides, how many of these cubic inches, 1 by 1 by 1, can fit inside the rectangular prism above? Well, for this, you have to visualize it in terms of rows, columns, in 3 dimensions. Across the bottom, we'd have 3 rows of 2 for 6 on the bottom, but we have more than one of those layers. We have 5 of those layers stacked on top of each other for 5 inches. So 6 times 5 is 30 cubic inches. So what's the pattern here? How do we find the volume of a rectangular prism? Perhaps you can see that it's not just length times width like a rectangle, but it's all 3 dimensions: length, width, and height, all multiplied together, symbolized here with 3 letters L, W, and H. This is the formula for the volume of a rectangular prism. Always, always, always. And we can actually apply this to a more specific case which I'm going to have you do on your own right now, what would be the formula for the volume of a cube? That is, the length is just s, the width is just s, the height is just s. The same value, length, width, and height. How could you derive a formula that describes that relationship? Take a moment to do that now. Welcome back. We briefly introduced the concept of exponents near the beginning of our lecture today, but we're seeing it show up here again. As we see the volume of a cube, s times s times s can be summarized all the more elegantly as simply s to the third power, s cubed, as we say. Interesting that we call it cubed because that's exactly what this describes, a cube with a length, width, and a height, all of the same value. A certain length, s cubed. And so there's our formula for the volume of a cube, even more simplistic. V equals s to the third power. Always true. Always, always, always. Now, in some of the word problems, you may have also noticed that there are certain phrases that indicate different kinds of mathematical operations. For example, here I'm showing you a set of phrases down the center of the screen, and on the left-hand side I'm showing you a column for addition, and on the right I'm showing you a column for subtraction. Let's take a look at each one of these, and each one of these phrases belongs either in the column to the left or in the column to the right. Let's take a moment to figure out which ones go where. The sum of, well, that's addition. Less than, that's subtraction. Decreased by, that's also subtraction. Subtracted from, that's also subtraction. Total or plus, obviously addition. Difference between, that's subtraction. Increased by, that obviously indicates addition. More or more than, well, that's addition again. Added to, again addition. And exceeds, that's also addition. So you can see that there's a set of words that you've probably known all along indicate one particular mathematical operation or another, but now you're consciously aware of it. Here's another set. Expands, addition and subtraction, that's addition, isn't it? Diminished by, that's subtraction. Take away, also subtraction. Reduced by, also subtraction. Greater than, that's addition. Minus or less, that's subtraction. Gain or profit, addition. Longer, also addition. Older, also addition. And heavier, once again, addition. So we've done this with addition and subtraction. Let's also do it with another set of addition and subtraction. I thought we were going to go right to multiplication there, sorry, but let's do one more list of words there. Wider, that's also addition. Loss, subtraction. Lower, also subtraction. Shrinks, subtraction. Taller, addition. Smaller than, subtraction. Larger than, subtraction, addition rather. Younger, subtraction. Slower, subtraction, and shorter, subtraction. All right, now we get to move on to multiplication and division here. And this might be a little more difficult than some of the previous ones that we were doing before for addition and subtraction. Times, perhaps you already know that that indicates multiplication. Divides, well, that's obviously division. Divide by, also division. Divide into, also division. Multiplied by, also multiplication. Half of. Now what's interesting is when we get into halves, there's actually two ways of thinking in terms of half. One is division, one is multiplication. In this case, we're specifically talking about half in terms of dividing by 2, and that's a clue. That's division. The word of actually indicates either multiplication or division. Which one is it? If you have 2 or something, or 5 of something, or 10 of something, what are you actually doing quantitatively? You're actually multiplying. So of is actually indicative of multiplication. If you're taking a third of something, well, specifically if that means dividing by 3, that's division. Per, miles per gallon. How do you calculate miles per gallon? Well, you take the number of miles that you've driven and you divide that by the number of gallons of gasoline that you've burned. So per indicates division. How big is each part? Well, that's also division. How big is each part? Well, when we're talking about something going into something else, we're talking about parts making it into a whole. So if we take a whole and divide it up into a set of parts, how big is each part? That's a process of division, isn't it? The product is, when you see the word product, that always indicates multiplication. How many parts can be made from? Well, if you're dividing something into parts, that's pretty indicative of division. Twice, if you're doubling something, well, that's 2 times something, that's multiplication. Also, if you're doubling something, that's 2 times. If you're tripling something, that's 3 times. Half of something. Now, we've seen half before in terms of dividing by 2, and that's obviously division. But we can also describe taking half of something. Half of something. There's that word of again. Of, which indicates multiplication. Dividing by 2 is actually the same thing as multiplying by the fraction 1/2. Half of, in terms of half times that, well, that's multiplication. So we can also describe a third, not as dividing by 3, but as multiplying by 1/3. And so once again, that's multiplication. So all of those phrases have a particular implication when it comes to mathematics. They indicate one particular mathematical operation or another. And so I've actually indicated a place here on the last page of your activity sheet where you can take a moment to write down each one of those, maybe not all of those particular words that we went through, but some key ones that you noticed before that are of significance to you. Perhaps rewind the video a little bit so that you can go through some of those again, but reinforce some of those words as being indicative of addition, subtraction, multiplication, or division. Take a moment to do that now, please. Welcome back. In a very short amount of time, we've gone through some very important and vital foundations of all of algebra. We've described order of operations. We've described some basic formulas for perimeter, area, and volume. We've described the steps involved in solving word problems. And we've described how sometimes particular words indicate some particular mathematical operations over another. That's a lot of stuff, and it can be pretty overwhelming to think of all of the things that we've gone through. And so what I'd like for you to do is to summarize what it is that we've done today. And here's how you do it. I want you to take a look at your activity sheet and go through it and indicate, perhaps with a star, perhaps with a highlighter, the most important things that we covered today. Perhaps the practice problems are not things that you would be highlighting, but perhaps those steps in solving word problems, those would be things that you'd be highlighting. See if you can find some other things that would also be highlighted. This is an important step in being able to effectively study mathematics, not to mention to be able to study effectively in college. This is a very important tool. At the end of each one of not only these videos, but also each of the classes in our math class, as well as even all of your classes that you take in college, take a moment to go through your notes when you're all done and summarize, make asterisks, make comments, make stylizations here and there to indicate what things are the most important. What are the things most important to remember that will reinforce in your mind those things that you need to remember, and it will make it so that learning becomes all the more effortless. Hopefully that's pretty straightforward and you didn't need a whole lot of time to be able to do that, but that's a skill that I want you to make use of as time goes on. Hopefully this was a good experience for you. I'm going to try to continue to make videos as we're going through the course together. Hopefully I'll do a little bit better next time than I did this time. But until then, take care.